Good afternoon. It is indeed an honor for me to participate in Ocean Acidification Week, and I want to thank the organizing committee for allowing me the opportunity to talk about ocean acidification from a global perspective. Today I want to address the physical and chemical processes that affect acidification in the global oceans and to address a little bit some of the biological responses that occur there. Over the course of the last 2.5 centuries, approximately 2.5 trillion tons of carbon dioxide have been released in the atmosphere from the burning of fossil fuels, coal, oil, natural gas, deforestation processes, land use changes, and cement production. And about 25 to 30% of this carbon dioxide has been taken up into the ocean in a process called ocean acidification, whereby CO2 reacts with water to form carbonic acid, and that carbonic acid dissociates to form a hydrogen ion species, which causes the increased acidity. Now, the NOAA Earth System Research Laboratory has been monitoring the atmospheric concentration of CO2, and this representation here shows the zonal mean CO2 concentration from the South Pole on the left to the North Pole on the right. And this snippet of the data from about 15 years shows the gradual increasing concentration of CO2 in the global atmosphere on a rate of on average of about 2 parts per million per year. You can see the breathing of the Earth with the uptake of carbon dioxide in the summertime to plant growth and to the release overall in the wintertime due to respiration. And for pH in seawater, we can look at this a little bit further from the work of Lichter et al., who showed us from model outputs that about 88 of the world's oil producings contribute to as much as 55% of the global pH change in the oceans between 1800 and 1850. Which really addresses the question of how will these pH changes in the surface oceans affect organisms and the marine communities that they represent. So the Global Carbon Project has been addressing this issue by developing an annual update of the inventories of carbon dioxide from release from fossil fuels and land use changes, and comparing that directly to the ocean carbon sink, the land carbon sink, and the increase of CO2 in the atmosphere. And the questions they are trying to address are, can the oceans continue to keep this pace with the atmosphere? And if so, for how long? What controls the seasonal and decadal variations in carbon uptake and pH changes? How will future changes in circulation and biology affect the uptake mechanisms and global productivity? And how will the changes in the carbonate system and pH have an impact on marine organisms and marine ecosystems? So in order to address this, the Ocean Carbon Community has worked together with the Ocean Acidification Committee to develop a global ocean acidification observing network that consists of carbon measurements on repeat hydrography cruises, the blue lines for example, on surface observing ships, showing here in the green lines, and on moorings and fixed sites, and now on autonomous platforms. And this international partnership has 3 major goals. The first is to document the status and progress of ocean acidification in the open ocean, coastal and estuarine waters, and in coral reef environments. The second is to understand the impact of ocean acidification on diverse marine ecosystems and societies, and to support the forecasts of ocean acidification conditions into the future. This slide is from the IPCC AR6 Working Group 1 report that just came out this summer, and it shows the changes in pH over time at a number of different oceanic sites where long time series have been measured. And what you see from this slide is that everywhere we look at these long-term data sets, there is a declining surface pH in the water column due to the uptake of the anthropogenic carbon dioxide from the atmosphere. And that, in general, has a rate of a change of about 0.002 pH units per year. Now, we can look at the physical drivers of those changes that are taking place and seeing how that affects the rates of change of pH in the oceans. And this slide shows some of the effects of temperature and gas exchange on the pH distributions. The left-hand side is from Kai et al. 2020, and what they show from a theoretical basis, in a closed system, the pH decreases as the temperature increases. However, in an open system, such as the surface ocean, that process, which is really quite fast, taken on the order of minutes to days, is counteracted by gas exchange, and that gas exchange tends to drive the system towards equilibrium with respect to the atmosphere. But that process is quite slow and takes on the order of 6 months to a year or so. And so the residence time of the water and how it responds is quite important to this. In a short residence time, the impact of the temperature would be most important, and in a long residence time, the impact of the gas exchange would dominate the system. So when we look at the distribution of pH in surface waters, what we tend to see from the center plot from Zhang's work in 2019 is that the pH values are generally highest in the high latitude regimes, and they tend to decrease as expected when you get to the warmer tropical waters. And so the overall effect then is a very small impact of temperature on the pH in the water column in these regions where there's long residence time. When way we get at these detailed pH measurements on a global basis is by taking the Surface Ocean CO2 Atlas, the SOCAT Atlas, which makes measurements of PCO2 and total alkalinity, or estimates of total alkalinity from salinity, throughout the global oceans over the past 40 years. And we have acquired as much as 23 million observations. And through the thermodynamic relationships, we then calculate the pH. Similarly, from the Global Ocean Data Analysis Project, or GLODAP, from the repeat hydrography cruises, there have been additional 15,000 observations in surface waters, which were taken from DIC and alkalinity measurements, and the pH was calculated from that. And the results are shown here with the SOCAT observations on the top and the GLODAP observations on the bottom. And what you see, again, is a very clear agreement, for the most part, on the global basis. A little more detail in the Arctic zone where there's more observations. But you see higher pHs in the Arctic and Antarctic, and lower pHs in the tropical regions. Now, a clear striking relationship occurs in the tropical Pacific and Atlantic, and along the coast of the western boundaries, where the residence time of the water is quite short, and so therefore in these regions you do not see an equilibrium with respect to the atmosphere, and the pHs are quite different because of that, and this is a product of that short residence time of the water, amounting to weeks or so. Now, Li-King Zhang just took that same global data set and represented it in terms of decadal changes in hydrogen ion concentration over the last 40 years or so, by breaking the data up into decadal increments, and the maps are shown on the right hand side, and the decadal means are shown on the left hand side. And the agreement between the observations and the models are really quite good. They show a very good agreement, at least through the present. And what you tend to see is large changes occurring in the high northern and southern latitudes, and smaller changes in the tropical regime. When we look at the same relationship for carbonate ion concentrations, we get a very similar results occurring there as well. Again, real strong agreement with the models, but it also suggests that by the time we get to about the next couple of decades in 2030 and 2040, we might actually, from the observations alone, be able to see the difference that will occur under a low CO2 emission scenario and a high CO2 emission scenario. So this is really very encouraging to us, and we're hoping to continue these very important observations into the future. A very wonderful piece of work was done by my colleague Masao Ishii, making time series measurements from ship cruises along 137 degrees east in the Western Pacific, with the ship cruises occurring twice a year in the winter and the summer, and allowing to get direct measurements of changes over different latitudes. And when you can see from these plots at 10 degrees north, 20 degrees north, and 30 degrees north, is you see long-term trends in increasing DIC, decreasing pH, and decreasing aragonite saturation. We can drill down on this in a little more detail to show, for example, at 70 degrees north, the rate of change of pH is on the order of minus 0.001 pH units per year, and for aragonite saturation is minus 0.007. But when we go to the tropical regions where the buffer capacity is higher and there's larger uptake of anthropogenic CO2, we can see indeed the normalized DIC concentrations increase significantly. pH decrease trend is about doubled, and the aragonite decrease trend is increased by about 70% or so. So we can see large systematic regional differences, primarily related to the changing buffer capacity of the oceans and its ability to take up carbon dioxide. If we look at our Ravel factor, which is a measure of that buffer capacity, we can see under different CO2 emission scenarios very dramatic differences in the Ravel factor, increasing from a background level of about 8 or 9 or so in the pre-industrial out to values as high as 14 or 15 under a high CO2 emission scenario by 2050 or so. And these changes are really quite important. So the CO2 emission scenario plays a major impact on the buffer capacity of seawater. And a good way of looking at that is, for this example, for a 1 micromole increase in DIC concentration at a Ravel factor of 10, the change in PCO2 would be about 2 microatmospheres. What we are seeing right now on the global average. But for a Ravel factor of 20, for a 1 micromole change in DIC, that would mean a change in PCO2 as much as 4 microatmospheres, meaning that the seasonal variability would dramatically change in the future from what it is right now. And here's an example of that in the global oceans from the modeling work of Zhang et al. And this is the model output for 1770 pH, and you see that the mean pHs are about 8.2 in comparison with 2000, where the average pH decrease is about 0.11 lower than what it was in 1770. And the differences you can see is very large differences in the high latitude regimes in the high northern latitudes compared to the high southern latitudes due to this change in the buffer capacity, decrease in the buffer capacity in the high northern latitudes, and much smaller changes in the tropical regime. Now, you can look at this for what would happen at any given location, and this is demonstrated here from the work of Pacella et al. And what the suggestion is that when you go from the pre-industrial to 2100, you might see as much as a 0.4 pH drop, but also you would see a very large change, a large increase in the amplitude of pH. And that increase in amplitude of pH means that you, in higher variability, then you tend to drop below some critical thresholds sooner rather than later. So the change in the amplitude of the pH has an impact on the time that you would actually see a drop below a critical threshold. Now here is a global mean distribution of pH represented on a map based on combining the PCO2 data with the GOA-ON ESM2 model output. And you see that by about 1950 or so, you begin to see a significant drop in pH. And by the time you get to 2010 to 2030, that drop accelerates dramatically, such that the overall trend in pH over time goes from a value about 8.2 in the pre-industrial to a value about 7.7 or so in by 2100. So this is a very, very dramatic change that will be occurring over time. And a way to look at this is under an RCP of 8.5, you can take the decadal snapshots as shown here, and you can see with each change, decadal change, you can see that the overall mean average pH and hydrogen ion concentrations have dramatically changed throughout the global oceans on an RCP of 8.5. But when you do that same analysis for an RCP of 4.5, the situation is quite different. So under an 8.5 scenario, you'd see as much as a 0.33 change from the present day to 2100 in pH, and that would be an equivalent to about 114% increase in the hydrogen ion activity in the surface ocean. Under an RCP of 4.5, the pH change would be much smaller. It'd be about 0.13 over the course of this century, and the equivalent hydrogen ion activity increase would be on the order of 37%. So a very significant difference given the two extremes in the CO2 emission scenarios. Now, the IPCC report went on to show what the impacts of these CO2 emission scenarios would have on the atmospheric concentration shown on the left, the oceanic uptake rate shown in the middle, and the land uptake rate shown in the far right-hand side. And what we see is that for these high CO2 emission scenarios, you see a very dramatic change in the atmosphere, going from about 400 as it is today up to as high as 1100 microatmospheres. And you can see some impacts of reducing CO2 emissions under 2.6 scenario, where the CO2 levels in the atmosphere can begin to drop off in the second part of the century. With respect to the oceans, you can see that the rate of carbon uptake in petagrams of carbon per year also is a strong function of the CO2 emission scenarios, where it will increase up through about 2030 or 2040 under 2.6, and then begin to decrease fairly quickly. But under a higher CO2 emission scenario, it will continue to increase out to about 2070 or so before a decrease begins to occur. But under all these scenarios, the oceanic inventory, the total amount of carbon dioxide that's stored in the ocean, continue to increase throughout the entire century. And so we are seeing a significant difference between the different outputs from the various CO2 emission scenarios. The model, most recent model projections from Kwiatkowski et al., going from the present day temperature increases under the 2.6 and 8.5 scenarios, and on the lower panels, the pH differences for those same two scenarios shows that in a high CO2 scenario, the temperature increase in the top right-hand panel would be as much as about 3.5 degrees C on a global basis. And for that high CO2 emission scenario, the overall change in pH in surface oceans would be at least about a decrease of around a 0.4 pH decrease. Now, for aragonite saturation state, things are a little different. The saturation state tends to increase with increasing temperature, and the effect of gas exchange tends to enhance that overall process, such that you have large differences between saturation state from the cold waters of the Arctic and Antarctic region to the warm waters of the tropical regions, ranging from about 1.3 or so to about 2.2 in the cold water regions, and from about 3.0 to about 4.5 in the warm water regions. So saturation state is a very strong function of temperature and shows a very striking correlation with temperature. Now, this can be shown here as an example from Sassi's work to show that the seasonal changes will also be dependent on temperature, with the range of increasing from the winter time to the summertime, ranging anywhere from 0.1 to 0.5 in saturation state, depending on location and the variability of the temperature difference between winter and summer. Another consideration is, when do you first occur of aragonite saturation state dropping below the level of 1.0. In a time frame of very low variability, you might expect to see a very short difference between the first occurrence of the undersaturation to the annual mean being below the undersaturation state. Under low variability regime in the bottom panel, you can see that time difference is quite small, but in areas where the temporal variability is large, that time difference would be quite much longer. So that consideration of the time differences are particularly important. And that is true also for the fully undersaturated condition. Under conditions of low variability, that will also be quite short compared to the time frame of the longer variability. And so we can look at this from the perspective of, when will we first see in surface waters undersaturation occurring? And this is from the modeling work of Steinacher et al. In 2009. And in the Arctic Ocean, the prediction from models was that first occurrence would occur somewhere around 2016 or so. In actual fact, it occurred a little bit earlier than that, about 2008. So pretty good agreement there. The entire Arctic Ocean would become undersaturated somewhere in the neighborhood of about 2040 or so. And in comparison with the Antarctic Ocean, the Arctic is a little bit more rapid. The Antarctic Ocean would begin to have the surface waters become undersaturated right around 2035 or so, and become fully undersaturated somewhere around 2070 or so. So there is a little bit of difference between the Arctic Ocean and the Antarctic Ocean. And in the tropical oceans, you see that they would remain supersaturated throughout the entire century, but there would be very, very dramatic changes in decreasing saturation state, probably dipping below some critical thresholds for marine calcifiers such as coral reefs. Here is a global representation of the aragonite saturation changes over time. Not much happening until about the 1900s, when you begin to see a significant decrease in saturation state globally. And then by the time 1950 turns, you see more dramatic decreases. And that begins to go even faster by 2040 or 2050, such that by the end of this century, the surface ocean are undersaturated in all of the Arctic and parts of the North Atlantic and North Pacific, and the surface waters become undersaturated in most of the Southern Ocean as well. When we think about what may occur in the subsurface ocean, we refer back to the global repeat hydrographic surveys as represented here by the recent paper by Gruber et al., demonstrating the increase in anthropogenic CO2 concentrations in the global oceans from 1994 to 2007. And we can use this information to validate the model projections of the anthropogenic CO2 uptake by the oceans. The black lines represent the modeled estimates of the uptake, and the cyan lines show the estimates from the observations themselves, and superimposed on that are the ocean interior observations from Ghost Ship. And there's fairly good agreement that at present or so, the uptake averages about minus 2.5 petagrams carbon tier uptake into the ocean, with an uncertainty of about 0.5 petagrams of carbon. And what this suggests then is that the current ocean uptake of 2.5 to 3 petagrams of carbon per year is keeping pace with the atmosphere, and the total inventory of anthropogenic carbon in the oceans is about 170 petagrams of carbon through 2019. We can visualize this from the very nice work of Brendan Carter and showing the anthropogenic carbon inventories in the Pacific Ocean. And you can see that the largest amount of inventory of anthropogenic carbon resides in the subtropical western southern hemisphere and in the northern hemisphere. And the concentrations of anthropogenic carbon inventories north and south of that diminish, because most of the flux is from the high latitudes into the ocean interior in the subtropical regions. And here's a nice representation, that visualization from 1995 to 2017. And you can see the buildup, three-dimensional buildup of the anthropogenic carbon, particularly in the western, northern hemisphere and southern hemisphere. Now, recently the IPCC published the results of Lausette's inventories of the changes in pH penetration from anthropogenic sources down into the ocean interior, and the changes in aragonite saturation state. And throughout the global oceans from these transects, we can see the penetration ranges from about 500 meters in some regions to as deep as 3,000 to 4,000 meters in the high latitude convection zones of the North Atlantic and the Southern Ocean. And these changes that we are seeing are quite dramatic and quite significant for both pH and aragonite saturation state, amounting to pH changes that are significant all the way down to these depths. And the aragonite saturation changes on the whole range from about decrease of about 0.5 to 0.7 in surface waters, and then again penetrating down to these deeper depths. Now, thinking about what the biological impacts on the global oceans are, I referred to the recent paper by Jean-Pierre Coutusseau et al. That summarizes the conditions for a high CO2 scenario on the right-hand side and a low CO2 emission scenario on the left-hand side, suggesting that for a low CO2 emission scenario, we might expect to see about a 1.2 degree increase in temperature over the next century, 0.14 decrease in pH, and about a 0.6 meter change in sea level. And this would have an impact on some organisms, particularly corals and pteropods, but the impacts on many of the other species would be still reasonably mild. Whereas in a high CO2 emission scenario of 8.5, we would see strong impacts on many different species of pteropods and bivalves, fish and shellfish, seagrasses and mangroves, and the overall impacts on the coastal systems, coral reef systems, fisheries would be quite severe. So we have a choice, and that choice is to whether or not to do our best that we can to reduce these CO2 emissions and certainly avert the most serious impacts of climate change on our marine ecosystems. And I think for ourselves, it's really important for us as scientists to convey this information to the public and convey the importance of addressing the CO2 problem with respect in particular to the marine system. Another example, a most recent example of the biological effect of acidification on marine organisms is a recent paper that just accepted for publication based on the P16 data in the North Pacific, showing the impact of that shoaling saturation horizon in the North Pacific in terms of its impacts on the types of dissolution that occurs within marine pteropods. And what it shows is that when the undersaturation zone shows above 100 meters, in this case about 70 meters, you see type 3 dissolution occurring in many of the samples from this cruise of pteropods. But when that saturation state gets deeper, either to the east along the east-west section or in the north-south section to the south, then that impact of dissolution is greatly abated. So there's a very strong sensitivity of the pteropods to the saturation state changes that are occurring. So in conclusion, our major challenges determine anthropogenic ocean acidification changes and the biological responses that occur simultaneously against a backdrop of increasing natural variability. The rates of acidification and seasonal variability will increase with increasing CO2 emissions and will be clearly measurable in regional variations, particularly in the high northern latitudes as opposed to the southern latitudes. And the rates of decrease in the aragonite saturation state will slow down in the higher latitudes, but with increasing CO2 emissions, they will go well below the critical thresholds during the course of this next century. And finally, the biological effects of acidification are occurring now and are measurable now and will be much severer if we undergo a high CO2 emission scenario towards the end of the century. I want to leave you with two quotes. This is the picture of a sunset on my deck, and normally under good conditions you would be seeing the Olympic mountains. On this particular occasion in the late summer, we don't see the Olympic mountains not because of cloud cover, but because of smoke from the forest fires. And I'm reminded of that, of the words of Wally Broker, who said in 1998, "Climate change is an angry beast which we are poking at with sticks." And clearly we are seeing the effects of the effect of humankind on climate change from the really severe warming that we saw this past summer, from the hurricanes' intensity and duration and amount of flooding that occurs, through the additional forest fires and the impacts of those fires. So the impact on humanity has really become very clear to all of us, and it is really quite severe, and it's something we need to address right away. Finally, I also want to give this quote from my dear friend Carol Turley, who said about a decade ago that human footprint in the oceans is now clearly detectable. It is warmer, it has increased acidity, and it's less diverse. And I think this is an important message for all oceanographers, is that we need to be addressing these issues right now, and we need to communicate the importance of these changes to the global community. Thank you, and I appreciate the opportunity to discuss this further with you. Thank you. 35 minutes.